So these two things should be noticed in the lattice wave. Okay? And if you plot this eigenfunction and eigenvalues, just like as we did for the particle in a box, then say n 0, the ground state, the eigenvalue is half h bar omega. Eigenfunction is something like this, okay? And then the probability finding a particle is going to just like this, okay? That is the plot of this equation, okay? And when it's excited, then eigenvalue now becomes 3/2. And then the wave equation is going to look like this. And then the probability of finding a particle now becomes something like this. So actually at the center, there is no atoms we can find, the phonons, in other words. Okay? That is quite different from the classical theory. In a classical theory, when the oscillator is oscillating in between the x naught plus x naught and minus x naught, so that the total length, let's say, that is 2x naught, then the finding of, in a classical theory, what we can see is that at the center, the kinetic energy is maximum. Kinetic energy is maximum. So that we cannot see any, there is a very little chance to find a particle at the center. But at the edges of the oscillation, here the potential energy is maximum, right? Which means this oscillator, it just stays there. So in the classical theory, it says that we have a maximum probability of finding this oscillator at the ends, and then we have almost zero probability of finding this oscillator at the center, because the kinetic energy is the maximum, right? It's moving very fast at the edge, and it just stays there at the both ends. That is the classical theory probability. But in a quantum approach, it says that, and when it's in the ground state, at the center we have a very big probability, and first excited, then the zero probability. Now let's see what happens if it is excited more. Then we are going to have 5/2 h bar omega, and then this wave equation now becomes something like this, okay? And then the probability of finding this particle now becomes something like this. So when it's going to be excited more and more, now the finding of, but the probability of finding a particle now becomes approaches to the classical theory. So we call this correspondence principle. Right? So this just says that when the atom is excited, the atomic energies, okay, the energy is related to the lattice atom, the phonons, is different from the energies of electrons in space, in a confined space. So that's why if you increase the temperature of the furnace, the nickel wire, you apply a high electric potential to the nickel wire and passing a high current, then it becomes red, and even it becomes yellow as the temperature goes high, but it cannot emit an X-ray. Because when the external energy is cut down, it can return to the original energy state, to the ground state, like a staircase, okay? Like this fashion. Always the H bar omega next available energy is available for this case. So it cannot emit a high energy like X-ray. But in a particle in a box case, you see when it's excited very high, the step next available energy state, this is very large, like an order of 10 to 16 electron volts or something, right? And then the next is less than this, but it's still high, and then something like that for the particle box. So that's why it can emit X-rays. But the furnace, the lattice atoms, phonons, the movement of atoms rather than electrons, it cannot emit an X-rays because of this. And then they can be explained by the Schrödinger equations that we developed, right? Okay, the next topic, I hope you can read the textbook where it is related to the phonon energies, H bar omega, okay, the vibration states, and it has a vibrational mode, and it even talk about what is the average number of phonons expected in the lattice with the frequencies omega m in equilibrium at temperature T. Something like that. That is a very important questions you have to answer, right? And then from that question, you can have the statistics for the phonons. That is for the electrons, Fermi-Dirac statistics. But for the phonons, Bode-Einstein statistics. That is going to be covered later. But with this, in this chapter, it has some thoughts, explanations about how many photons are available at a certain temperature, things like that, okay? And then that the number of phonons at a certain specific energies is related to the statistic, probability of the energies. So you just read it. It's kind of complicated, but it is important. So it's not going to be covered in the class, but you just read it at home, okay? And the next section is the hydrogen atoms. We start out with the string, and then we cover the lattice wave, light wave, and matter wave. And in the matter wave, we have we use the Schrödinger equations, and with that Schrödinger equation, it has the potential energy in the equation. And then we have set the 3 cases for the exact solutions where the free electrons, the potential energy is equal to 0, and the lattice phonons, lattice atoms, the potential energy is equal to 1/2 gx squared, right? Now, the last problem that we are going to discuss is about the hydrogenic atoms. Okay, in the hydrogenic atoms, it has potential energies, Coulombic potential energies. So in the Schrödinger equation, you're going to replace that, the potential energy, with the hydrogenic Coulombic force, like potential energy is Q square over R. This is a proton, and one electron is going to circulate, orbiting, and then the distance is R, right? And force is Q square over R square. And the potential energy is going to be Q square over R. That is the potential energy. So the Schrödinger equation for this hydrogenic atom now becomes h1 square over 2m applying psi plus minus r q square over energy, that is the potential energy of psi is equal to 0. That is going to be the Schrödinger equations. And as you can see, the Cartesian coordinate x, y, z is not convenient in this case. Okay, so we want to use a spherical coordinate. Because the movement of electrons, or the energy of electron, is only function of the distance r in this case. So we're going to use x equal to r sine theta cosine phi, and y is r sine theta sine phi, and z is equal to r cosine theta. This kind of thing. See? And the solving that Schrödinger equation, we're going to have by separation of variables lead you the Laplacian is going to be in a spherical coordinate. It's going to be around r square, around r. It's just mathematics. R square sine theta round sine theta round r square sine square theta round phi square. That is the spherical coordinate. And then with the separation of variables, this Schrödinger equation can be solved minus 1 over psi round phi square round equal to A. A is a constant. And then 1 over sine theta, d theta, sine theta, d theta, d theta plus b minus a sine theta is equal to 0. And then finally, dr squared, d squared 2 over r, dr plus 2m h bar squared e minus 3r minus b over r squared r is equal to 0. We'll have 3 equations. Okay. And then with these 3 equations, we are going to develop a magnetic quantum number, an angular momentum quantum number, and principal quantum number. And then we finally add spin number. So actually, we are going to get those 4 quantum numbers out of that Schrödinger equation solutions. And then we're going to discuss about the physical meaning of those quantum numbers. In any sense, we are not going to go for details of this, but most importantly, the principal quantum number is the most important numbers among this, because it is related with the energies, energy states. Okay. The other thing is just different configurations, but not directly related to the energies of the electrons, orbiting electrons. So next week on Monday, we are going to talk about this quantum numbers briefly, and then focus on the principal quantum number to get a solution, the eigenvalues, the energy values, something like this. Okay? The particle in a box that is the electron in a solid, okay? The energy state is En is h bar square over 2m m pi over L square. So the energy state is going to something like this, right? Now we have seen that how many volts later we have seen that just ground state is 1/2, but after that is equally spaced. So that the energy eigenvalue is n plus 1/2 h bar omega, something like that, right? Now in hydrogenic atoms, if I solve this, and then from that principal quantum number, what we are going to have is a solution we're going to have the energy in this case is mq force 2h bar square 1 over n squared, something like that. So it means that at the ground state 1s, and then huge separation to the 2s 2p, and then the next is somewhere 3s 3p 3d, and then the next, and then the next thing. The energy separation is going to look like that, which is quite different from the other two cases, right? And we are going to get this results, or this principal quantum number, which is obtainable from the equations coming from the Schrödinger equation by the separation of variables. Okay, so we're going next Monday. We're going to get this eigenvalues, and each electron in a solid Pauli exclusion principle. This Pauli exclusion principle says if the electron is confined in a system, closed system together, no electron can have a same energies. All the electrons have different energy states with these four combinations. Okay, one of these may be same, but all